Assalamualaikum warahmatullahi taala wabarakatuh. Today we from section 8 group B going to present about the motor speed control systems. So on the screen is our group members and their matrix number. So for introduction, I will talk about control engineering a little bit. Control engineering is the engineering discipline that focuses on the modeling a variety of complex systems such as mechanical system and control design that will make this system work as our desired output. So control engineering usually use feedback when designing control system. It is mostly achieved with the aid of the PID controller, which is proportional integral derivative. So usually the tools that control engineering use is a Matlab, which is a high performance technical computing language. It integrates computation, visualization, and programming into an easy to use environment where the familiar mathematical notation expresses and problem and solutions. So typical use of Matlab is on math and computation, algorithm development, modeling, simulation, and prototyping, data analysis, exploration, visualizing, scientific, engineering, graphic, application of development, including graphical user interface building.
Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi. My name is Mahmud bin Juno, CD160050. I'd like to present about my part, which is chapter 2, in the part of theory. So we go through to the next slide. Alright, as we can see, DC and AC motor have a difference in as you can see in figure, type of motor, which is a direct current, which is DC, and alternating current, which is AC. So we can see the difference is, we can see from the circuit. So next, what is about AC and DC? AC and DC, which is the alternating current and direct current, are two main forms of charges powering our electric and electronic world. An alternating current can be defined as a flow of current that that changes its direction at regular interval, which is the period or regular interval at which an AC charges its direction is termed as its frequency, which is Hertz. Direct current is a flow of electric charge or electron that flow only in the one direction. If represented on the graph, DC can be plotted as a straight line as it does not change in direction. No frequency are associated with DC. Next, application of DC and AC. There are many functions of AC and DC motor, which is AC is used to power as the power of refrigerator, domestic light, fan, motor, and air conditioner, washing machine, and virtually all industrial machinery. And for DC is mainly used to power electronic and other digital equipment, smartphone, tablet, electronic vehicle, LED, and also run on DC that is converting from the usual AC power source. That's all for the theory. Thank you.
So I will talk about the procedure for the Simulink modeling for the motor speeds. So as you can see, this is the procedure of using the Matlabs. So start Matlab, blank model, simulations, and add blocks. We need 6 gain block, 2 add block, 2 integrated block, 1 in 1 out block, and those blocks need to be connected and labeled as shown as figure below. So this figure. So we jump to the Simulinks. So with the home tab, you click the Simulink part and also blank model. So from here, you can click this library and go and type the block that we needed. So this is add block. So we need integrator. This is integrator block. We need gain block. This is the gain block. we need in one block and out one block. So this is the out one block. So this is the add block integrator gain out. So using the given value, we need to take the amount of block that we needed and also arrange the model until we get like this. So this is the final of the layout of the PID controller. So from there we need to assign the parameter for each block. So as you can see, the gain block the gain block will be on the red outline because of the parameter is not been set. We need to set it in the command prompt here for the value of JBKRLs. So this is represent resistor inductance and so on, as shown on the left of the screens. Also, after we signed it, we can run it. So that's all the procedure for modeling part. Thank you.
Bismillahirrahmanirrahim. My name is Fahmidini bin Muhammad and my matric number is DD170010. So firstly, I will explain about how to get lag and lead transfer function value by using road locus. First, we have to key in the motor parameter here, and then we put in this command, and the road locus will be plotted. So here, so for simplify, I already set up the settling time and percent overshoot. To set up settling time and percent overshoot, just right click and design requirement, add new, and also click on a grid. So to add a lag compensator, we click on preference, option, and click on zero pole gain. So we see here value is 1. So to add the lag compensator, right click, edit compensator, and on the dynamic box, right click, add pole and 0, choose lag. So as we mentioned, we need to set up the value of PO and ZO. So to set up the real pole and real 0, click on this one and set up real 0 to -1 and real pole to -0.01. So as you can see here, the settling time is less than 2. So as I mentioned in the introduction or ni, we need to set up the settling time is less than 2 seconds, overshoot is less than 5%, and steady state error is less than 1% at 1 radian per second. So if you see here, the amplitude is not in 1, so we need to manipulate at the gain here, K. So we put around 10, and you can see it's changed the amplitude already at 1, but the settling time is more than 2. So in this concept is we use try and error. So we set the value at 14, and here we get this the settling time is less than 2 seconds, steady state error is less than 1%, and percent overshoot is less than 5%. Overshoot percent is less than 5%. So For the final result for the lag transfer function is 14 times s plus 1 over s plus 0.01 as stated here. So this is same goes to the lead setup. Just delete the lag me and then add poles and 0 lead. So we set up the real 0 to minus 35 and real pole to 1400. So as we can see is this here, the amplitude is already 1, but the percent overshoot is too higher. So we need to again set up it here. So by try and error, we get the value here is 5 e power of 5. So here the settling time is less than e, less than 2 seconds. Steady state error is less than 1, and percent overshoot, the lowest that we get is around 6%. That's all for lead and lag transfer function value. Thank you. Hello, my name is Fahmidini, and I will explain on how to make a Simulink control. So first of all, we can open a file from a Simulink modeling, and we get like this one. So we need to make sure all the variable here is list out or is will call. If the symbols here or is a block here is red, so we can call all the variable from the Matlab command view. It's just like here has been recorded. So second step is we need to put input here. So just right click, linear analysis point, and open loop input. Same goes to output, right click, linear analysis point, and open loop output. So it will appear like this one, a down arrow and upward up direction arrow. So to use a Simulink control, we can use a control system designer, and it will appear like this one, this window. So to plot a step response, you can click the new plot and choose a new step, and it will come out with this step response. Okay, so next we want to have a step response graph using a Simulink simulation. So from the existing block diagram, we can add this scope, step input and scope from the library, from this library from here. So you want to set is double click to the step response and set step time to 0, stop time 5 seconds, and then click run. So to want to see the result, you double click on the scope, and then the graph will be appear like this. So this is the motor step response. So next we will make a simulation to get a step response if we introduce a lag compositor in this model. So from the previous model, we insert a new block, which is summing block and lag compositor. To set up the summing block, just double click and insert plus minus. for the transfer function block, double click and set up 1414 and 10.01. After that, we set the time to 5 to 10 seconds and then run. Again, to see the step response graph or the result, double click on the scope and we get this graph. So we can see here the steering time is less than 2 and the amplitude is 1, and this is the overshoot percent. So next, we will introduce a lead compensator in this model. So to do it, we just copy and paste here. Here also copy and paste and insert max block and change this value of transfer function to E5 plus 1.75 E6, and this one is 1400. So as usual, sets time to 5 and click run. So to see the result, just double click on scope and we will get the result. So from the result here, we can see the yellow is the lag compensator and the blue graph is the lead compensator. So from this graph, we can discuss that lag compensator have a lower settling time, which is almost 2, but for the lead compensator is very fast, less than 0.05. Okay, that's all for lead and lag compensator. For the last simulation, we want to see the voltage that used for lag compensator and lead compensator. From the previous model, we just add a 4 more block with this U lag, U lead, Y lag and Y lead. Before we run the experiment, make sure we set the format of the block is to array. Okay, so run and then insert this command and the graph will be appear. So from this graph, we can discuss that for a lag compensator, we use a very low volt between 15 to 5 volts only in 1 second, but for lead compensator is around 1 point something power times 10 power of 5. It means it's very high voltage use in the system. So for a small scale model, we more use lag compensator because the volts use is very low and we can use a small component. Okay, that's all for Simulink control. Thank you.
Okay, greetings. Okay, today I'm going to present a little bit about procedure for Simulink. It's run by Geoffrey Jr. CD170117. Okay, carry on. Okay, first thing off, you want to start with opening Matlab. Okay, once you get into Matlab, in the command window, you type SST_NEW and a window will come out where you can see this. You can see this. This is the generic window. Okay, the generic block diagram will come out. Okay, next. Okay, from the simulation tab, you find library browser. From the library browser, you will see all the different kinds of blocks. Okay, so first thing first, what you need to do is you need to add the following blocks, which is DC motor block, current sensor block, control voltage block, electrical reference block, ideal rotational motion sensor block, mechanical rotational reference block, and also the step block. Okay, once you're done putting on all the blocks inside the diagram, you need to connect the blocks by creating lines between them, by connecting the inputs and the outputs, and not forgetting to label each of the connections. Okay, next we're going to assign the values to the physical parameters for the motor, of course. Okay, next. Okay, as you can see, this is the finished DC motor diagram. Okay, once you finish doing it, you click Ctrl T to run the block diagram, and you will come out with this result, which is the speed step response of the DC motor. Okay, next, moving on, we're going to create a subsystem. Okay, how to create a subsystem is first we need to Control A, which is select everything, and then we need to unselect a few blocks, which is the voltage block and also the the step block and also the scope block. Okay, after we unselect the two blocks, we press Ctrl G to create a subsystem. Okay, once we finish doing the subsystem, flowing through, we'll be setting up the controller for lag compensation. Okay, like usual, we'll be going to the source library to find some blocks. Okay, what blocks we need to add is the subtract block and also the transfer function block. Okay, once you add in the blocks, we make adjustment to the lag compensator block, specifically the transfer function block. Okay, next we connect all the loops and we run the simulation by pressing Ctrl T. Okay, as you can see, this is the example of the. This is not the example. This is the diagram block that has been finished. Okay, with all the lines connected. Okay, now we press Ctrl T to see the result. This is the voltage step response for the lag compensator. Okay, next. Moving on from lag compensator, we start with lag compensation. Okay, again, from the source library, we need to find a few blocks, which is a subtract block, transfer function block, and we need to copy also the subsystem. Okay, next, we need to make adjustment to the lead compensator model, mainly the transfer function. Make the connection to close all the loops. Okay, then you run the simulation by pressing Ctrl key. Okay, this is the finished block diagram. Okay, as you can see, from the block diagram, we will be able to generate this result, which is the voltage step response of the lead compensation. Thank you. That is all.
Alright, Bismillahirrahmanirrahim. Assalamualaikum. In this part, my name is Muhammad Ujino, CD 160050. I would like to present about discussion, which is more to about Simulink Simscape. Alright. So based on our result in the Simulink Simscape, so they are same, which is this figure is same in the report that we provided. So based on the result that was successfully get from Simulink Simscape, can we summarize as the use of Matlab in turn with Simulink? Regarding to the result that we get, we can discuss in the two sections, which is step response graph and control effort vs time graph. So this is a figure of block diagram of DC motor, and then it shows the block diagram of DC motor that we build and design. With the source of Simscape library, it is easier to provide this block diagram. Okay, next, this figure represent for block parameter DC motor 1, which is about a parameter. So we can see there are three settings that we can set for this design, which is for the one, which is the electrical top, second mechanical setting, and default. So we go to the first, which is electrical torque. So we can see from this figure, the armature resistance, we are set 1 ohm, and the armature induction we set of 0.8 H, and you can see the back EMF constant, which is 0.02 volt. Next, this is a mechanical setting, which is the rotor damping initial speed, not rotor speed. As we can see the parameter. Okay, next, this figure about a speed scope. So we can see the line graph yellow. So before we go through, blue line represent of lead capacitor, and the yellow line represent for lead capacitor. So this figure shows that the parameter set, which is 4 seconds, is required to achieve the horizontal trend, which is 0.2 speed, while at the second figure, which is next figure, which is here, the current and position scope, it shows the current and position scope after the simulation are running. The image shows the current and position scope line graph. The line shows that parameter set 3 seconds are required to achieve the horizontal trend at the 1 speed. As previously mentioned, the blue line represent for the lead capacitor, while the yellow indicate the capacitor lag. Here the lead block diagram, which is after we added with the other input, which is subtract lag capacitor, which is the lag capacitor 1 and next, and then the output here, which is scope 1. So next we go to the lead capacitor, which is this figure. This figure, you can see the lead capacitor diagram is the voltage, lag, and lead result of the output scope 1 for the lag block diagram that have been shown in figure above, which is T1, T10, and simple best option is the setup that we have been used. We can see it also started with the origin point, which is 0, and for the lead capacitor, the lead line are increased from the 0 to the 0.9, and have the little down peak at 1, which is here. It started to decrease at the point 2, which is here, and then back to the increased state when achieved to 2.5, and it started to the horizontal line at the point 4, but unstable until the end of result, which is point 10. For the lag capacitor, the line graph is already in plateaued from since point 1, which is here, and until the point 10. Okay, that's all from me. Thank you.
Okay, greetings. Today I'm going to explain about the result, which is done by Geoffrey Jr. CD170117. Okay, first moving on to modeling. Okay, in modeling, this is the model for our diagram for speed motor control. Okay, in the control side, okay, this is our result for step response on the lag compensator. This is our result on the step response on lead compensator in the control side. Okay, next is this is the graph control effort versus time in second. As you can see here, this is the result. And next, moving on to SimScape. Okay, from Simscape, we finish doing our block diagram of the DC motor. Once we run the program, this is the step response from speed scope. Okay, next, this is the block diagram of lag compensator, and this is the result, step response from the voltage scope in lag compensator. This is the block diagram from lead compensator. Okay, once we run the program, the result will come out. This is the step response from voltage scope in lead compensator. Okay, that is all. Thank you.
My part is recommendation. A motor-driven system consists of several components: the electrical power supply, motor control, the electrical motor, and a mechanical transmission system. For an example, the heating, ventilating, and air conditioning system in many buildings use single or three-phase electrical power control by timer and thermostat to drive motor. Each component of this system can be optimized for reliability and efficiency. This fact sheet is designed to help the management staff at your facility identify opportunities to improve drive system efficiency. The categories provide a series of steps for checking and each of the motor. Some of these steps require the one-time involvement of an electrical engineer or technician. Others implemented when motor fail or major capital change are made in the facility. Yet others involve development of motor monitoring, energy management, and predictive. First, maintain voltage level. Second, minimize phase unbalance. Third, maintain high power factor. Fourth, maintain good power quality. Fifth, identify and eliminate distribution system losses. And the last one, minimize distribution system resistance.
So in conclusions, our objective of this experiment is achieved and we are able to simulate using Simulink modeling, control and Simscape. So from these experiments, we set our objective as to analyze the system model and manipulate the parameter for the analysis purposes, and we can set up the controller of lag composition and lead composition and find the differentiation of both for both compensations, and analysis the step response for an open and loop closed loops. So the analysis shows that we are able to control a non-linear model by any linear feedback system as a PID controller. Also, its designs according to the procedure guided that using the mathematical model of PID system that we developed, which is we refer from the Matlabs and the websites. So lastly, we can say that we are able to design and building and analysis the adaptive motor speed control system by using this PID control system with Matlab software features. Thank you. So this is the result analysis for the modern Simulink. So the result for the analysis, we are successfully creating a PID controller systems, which is involved of this layout of the process, which is voltage as our input and the motor speed is our output. So this is can be compressed as a subsystem here. and label it as a DC motor, which is on the left is the input and on the right side is the output. So the parameter need to be assigned first for the resistor inductance, and also the damping inertia, like that. So all the values are manipulated by us. Also after assigning those parameter, the gain block are no longer in the red layouts, and it can be run for the next step of analysis. Thank you.